Next, we move to our first keynote speaker of the afternoon session. This lady is another, like myself, Galway native and a graduate of the University of Galway, although probably like myself, it was when it was known by another name. We won't go on about it. She's the Latham Family Career Development Professor at the Institute for Medical Engineering and Science at the Massachusetts Institute of Technology, MIT. Her work has been published in Nature Biomedical Engineering, Science Translational Medicine, Science Robotics and Advanced Materials, amongst others. She's the recipient of multiple awards, including the Wellcome Trust Seed Award in Science, a National Science Foundation Career Award, an NIH Trailblazer Award, a Hood Award for Excellence in Child Health Research, the LabCentral Ignite Golden Ticket, the inaugural Future Founders Grand Prize, and the Harold E. Edgerton Award for Outstanding Faculty Achievements in MIT. Please join me in welcoming Galway's own Professor Ellen Roche to the stage.
Thank you. Thank you, Grania, for the kind introduction, and thanks for the invitation to be here to Ted and Stephen. It's a fantastic opportunity. Okay, so I am going to talk about my research today, and I went a little bit rogue with the title, but I was asked to talk about soft robotics in healthcare. Before I start off, I want to thank the team here who have done all this work. I just get the privilege of telling the story, and my funders here. These are my disclosures. And we'll get started. So the vision of the group that I lead is to support and repair organs with intrinsic mechanical function. And we try to design solutions that integrate technology into these inherent complex biomechanics. We focused a lot on the diaphragm and the heart and these life-sustaining muscular pumps. This is a traditional kind of design, simulate, test, and translate process. So we want to have industry and clinical partners adopt our therapeutic strategies, but we spend a lot of time in the simulate test loop, and in that loop we establish insights into biomechanics, the pathophysiology, and mechanical influencers. My talk today will be broken into 3 different parts. I'll talk about mechanical augmentation of organ function, multimodal simulation of biomechanics, and structural or biological repair of tissue. And within those categories, I'll focus on the soft robotic aspects. So starting with mechanical augmentation of organ function, I started on this path over a decade ago when I started my PhD at Harvard. And I wanted to know, can we augment organ muscular pump function? So I was in the lab of Connor Walsh and Dave Mooney, and we built this sleeve that goes around the heart to augment cardiac pump function, ventricular function in heart failure. And we showed in porcine models that we could restore cardiac output back to baseline after inducing acute heart failure with pharmacological means. When I formed my own group in 2017, and along with Professor Emer Dolan, who's here in Galway, we modified the sleeve to a textile-based device, more efficient coupling to the heart. And again, we showed that we could increase augmentation of heart function in an animal model of heart failure. So then we thought, how can we apply this technology to a different clinical application? And we looked to the diaphragm. The diaphragm is another big muscular pump in the body. And we thought, can we maybe design an implantable ventilator that can assist diaphragm motion and mimic breathing mechanics? So the clinical problem here wasn't acute cases like COVID or something where people need ventilators, but for respiratory muscle weakness, degenerative muscular diseases, and diaphragm paralysis. We all know about ventilators, positive pressure ventilators and mechanical ventilators. They require a tracheostomy or a mask, and that interferes with quality of life. So we set about trying to design this diaphragm assist system that augments diaphragm function as a treatment option. Worked with a multidisciplinary team on this, PhDs, material scientists, clinicians. The design is that we have these implantable soft artificial muscles that can augment the downward motion of the diaphragm. This is a sagittal and coronal cross-section of the lungs colored in red, and at the base of them you can see the diaphragm motion. So we thought maybe we can put an artificial muscle above this to augment this function when it's failing. And we used, for the first proof of concept, very simple types of small balloons inside a mesh and we put one each side of the diaphragm. At the end of expiration, these would be relaxed, and the end of inspiration, they would be contracted to augment the downward motion. In this fluoroscopy video, you will see the air filling these actuators and moving the diaphragm below them down. In the image or the video on the right, the heart is shown in the orange kind of semicircle there, and you can see the diaphragm moving below it. And this was really nice because what we showed that we could do is assist the diaphragm, in this case, from induced model of respiratory weakness. So the top line shows the pressure that we were giving. This is pneumatic pressure, giving these soft artificial muscles. In the center, it's shaded gray there, a little bit hard to see, but that's when the assist was off. And you can see that the flow into the lungs is doubled, and the volume, or the tidal volume that the lungs fill with, is doubled. So we were able to demonstrate that we could rescue ventilation. This is in a large animal model. What we learned was that synchronization was critical. On the left is when the artificial muscles are independently actuated from the native diaphragm, and the improvement isn't as good. When it's synchronized, you get a really nice, repeatable improvement in function. And this is shown for 6 different subjects in the graph on the right, where the orange is synchronized actuation, and it's a less variable, better augmentation of performance. So we put a lot of effort recently into synchronization and how do we best sync this implantable ventilator. We've used flow, so we can use spirometry and use that to trigger the movement of these muscles, or we can actually look at the surface EMG on the diaphragm. So we conducted a study that's not yet published, but we looked where on the surface of the diaphragm will give us the best neural function, and we can use that to trigger the actuation of these elements. Of course, we keep working on this all the time. We're looking at simulators of the thoracic cavity, the abdominal cavity, patient-specific diaphragms, rib cages, and we have new designs of these actuators to improve the function. So more to come, but this was the first demonstration of an implantable ventilator that leaves the whole native diaphragm intact. We showed we can augment diaphragm motion, respiratory pressures, ventilation. This also has a biomechanical advantage over positive pressure mechanical ventilation because it's a negative pressure ventilation method, and it paves the way towards liberating the airway during mechanical ventilation and allows patients to be ambulatory or mobile. So then we switched to another kind of application, and this was in collaboration with our partners at Boston Children's Hospital. We became interested in a condition called single ventricle physiology. This is a condition where kids are born with 1 pumping chamber instead of 2. They have 3 different surgeries before the age of 5 to palliate this condition. And the physiology they end up with is 1 pumping ventricle that pumps oxygenated blood to the body. And then the return of deoxygenated blood to the lungs is passive through a shunt. This is called a Fontan physiology. This is unfavorable in terms of the dynamics of blood or the hemodynamics because there's only 1 pump instead of 2 in parallel. It leads to multiple deleterious effects. You get systemic venous hypertension or high blood pressure. You get problems with the liver, poor exercise tolerance, low blood oxygenation. And the blood flow in that conduit is actually synced with the respiration or breathing cycle instead of with the cardiac cycle like it would be in a biventricular physiology. And we became really interested in this reverse blood flow that happens during expiration. So we worked on making assist devices to combat that. We designed, prototyped, and evaluated active and passive devices to support this venous flow. We used extravascular peristaltic pumps that could generate flow from a no-flow state. And we looked at valves. So can we prevent the reverse flow down to the abdomen that's causing the problems with the abdominal organs? We also looked at computational optimization of what type of valve design would be best for these patients because it's a really unique hemodynamic circumstance. So we did a lot of CFD modeling to really optimize this bileaflet valve design. We can evaluate these devices on the bench. Here's a compression pump on the left and an expansion pump on the right. And we can actuate these in different ways, changing the sequence of actuation, the pressures, and how they work. This, again, is not an additional surgery. It's an active conduit instead of a passive one. So with these, we were able to successfully generate flow from a no-flow state, which is promising. But we really needed to understand it better. And with our clinical partners, we saw there was a need to build better simulators of this condition. So we looked at creating twins, a benchtop twin and a computational twin. Then we could tweak different parameters and understand the physiology more. We also wanted to clinically validate these simulators. So we set about developing a respiratory simulator. Here you can see a soft robotic diaphragm. This is moving down. We have explanted lungs in there, and you can see how they inflate and deflate with every respiratory cycle. We can tune the compliance of the abdomen and the thorax in various ways. And this was displayed in the Trinity Science Gallery in the plastics exhibition. And then we overlaid this physical simulator, with a, this is the computational model that we developed in addition to the physical simulator, where we used a lump parameter model for single ventricle disease. So we added another aspect to our respiratory simulator. Here we're using a flow loop. And in this flow loop, we take patient-specific data of the vascular anatomy, the reconstructed vascular anatomy, and of the diaphragm and chest wall anatomy. And we have different chambers to replicate compliance of the lungs, of upper body, systemic vasculature, and we put a blood analog through this. So now we have the ability to tweak different parameters like respiratory rate and respiratory effort and look at how that's affecting the flow in this conduit. We can put this upwards or supine, downwards, and really tweak things to understand this better. But we want to validate this clinically. So we had the privilege of working with 22 eligible patients at Boston Children's Hospital that had had the Fontan procedure as children. We had them do a breathing protocol in an MRI machine where they varied respiratory effort, went from shallow to deep breathing at a constant rate, and varied respiratory rate. So they went from slow to fast breathing. And all the while we measured with MRI the flow in their aorta and in the Fontan conduit. This is a schematic of the 8-minute breathing exercise that these patients were kind enough to volunteer to do while in the magnet. And we had an app to help them to breathe, like a meditation app that you'd see on your Apple Watch, to help them to breathe in this way. And what we found was that increasing respiratory rate really increased the amount of backward flow to the abdominal organs. In addition to that, increasing respiratory effort, so going from shallow to deep breathing, had the same effect. And this was pretty new to even the surgeons that work there, because they hadn't done a direct study to look at these types of breathing interventions. So this can help with understanding better how breathing affects these patients. Nicely, we were able to show, and here we just show for peak flow rate, that our in vitro, our physical models and our computational models in silico and our clinical measurements match up really nicely. So for respiratory rate and respiratory effort, we show the same trends. So that was really nice and validating for these simulators. Eve Sheridan is a graduate of biomedical engineering here in Galway, who is now doing her graduate studies at MIT, and she's worked on an in-scanner ergometer. So she's built this ergometer that's non-ferromagnetic that can go in the scanner, and we can look at what's happening to the flow in the conduit during exercise, which is super interesting to our collaborative team. Okay, I'm going to move to the next section. We're okay on time. Here, I'm going to talk about simulations of biomechanics. So we do this with physical models and computational models. I'll focus here on the physical models. So one example is a biorobotic heart model for mitral valve simulation and intervention. The mitral valve is really beautiful. The apparatus has papillary muscles and cords and mitral valve leaflets. And very hard to replicate this with synthetic methods, with 3D printing or anything like that. So we wanted to retain this anatomical structure, but we wanted to create a benchtop model that would move for better testing of interventions. There's a lot of work gone into mitral valve repair and replacement technologies in industry. And really our goal was to create a model to test those interventions on the bench. So what we did was we created this biorobotic model where we preserved the anatomy from an explanted porcine heart. We removed, carefully dissected the myocardium and replaced it with this soft robotic cardiac muscle with muscles oriented in a very precise architecture. We could then connect this to a mock circulatory loop where we could vary compliance, preload, afterload, and measure a lot of different parameters. This is what it looks like in the lab. So we have a control system and we have flow meters and pressure sensors in the whole system. This is also compatible with clinical imaging like echocardiography and with direct visualization. So it allows us to directly observe intracardiac motion and device interaction. So here's the Frankenstein heart beating on the bench, and we're able to recreate left ventricular pressures, left atrial pressures, and aortic pressures, as well as measure flow through the aorta and through the mitral valve. Inside, we can put an endoscopic camera inside, and we can look at aortic valve motion. We can also measure it with ultrasound, and we can look at mitral valve motion. This is nice because we can perfuse it with a clear fluid, which enables direct visualization. The motion is all generated from the soft robotic myocardium. We don't have to connect this to any external pulsatile pump, which would lead to paradoxical motion. So here you can see how the left ventricular wall motion drives the papillary muscle approximation, and you can see the mitral valve closure. So we use this for not only replicating the healthy condition and the healthy biomechanics, but also for disease biomechanics. So acute mitral regurgitation is a condition where you have leakiness, basically, of the valve, and you get flow in the wrong direction. We were able to induce that by severing the cords that attach the papillary muscles to the mitral valve leaflet. So for moderate regurgitation, we could cut one cord, and for severe, we could cut more than one. And we ended up being able to show that you can get more leakiness or flow under the x-axis here, under the 0 point on the x-axis. That's regurgitant or backward flow. And you could increase the amount of disease that you could simulate on the bench. And then, of course, we looked at different ways to repair this or replace it. We tested a variety of different devices from companies, like we tested MitraClip and NeoCord and mitral valve replacements. Here, I'm just going to show the trifecta valve. So pre-treatment, and here you can see this valve with these flailing leaflets, a lot of leakiness, and then post-treatment you get this nice coaptation of the leaflets and you don't have any mitral regurgitation. And you can quantify that, so you can show here in the center we have a lot of backward flow, that's quantified on the right, and then when you put in the valve you can bring it back to baseline. So a nice quantitative way both to train interventionalists and also to understand the biomechanics and to test devices. We went on to do another type of simulator for aortic stenosis. Aortic stenosis is a condition of the aortic valve. And here we wanted to incorporate it with living preclinical models. So in aortic stenosis, the valve becomes narrow, doesn't allow enough blood through, so you get a high pressure gradient across the aortic valve. And it can be from congenital or degenerative causes. And we really wanted to come up with an accurate way to mimic aortic stenosis with high controllability. So we made this sleeve. It's a thermoform sleeve with a fabric backing. It has 3 different pockets that can be independently actuated. And we can adapt it and adjust it to go around the aorta. We did this in a porcine model where we could measure cardiac function at day 0, implant the sleeve, look at MRI and further actuation at day 6. And then at day 8, we could catheterize it. So we get this pressure volume loop and measure cardiac function again with ultrasound. And here you can see some computational modeling of the sleeve being actuated and deactuated, and 4D MRI flow measurements of the sleeve with 3 pockets or 1 pocket or 2 pockets filled. So you can get very different morphologies in the cross-section and very different flow profiles. So you can create disease models. The PV loop or the pressure volume loop for 1 cardiac cycle is shown on the bottom. And you see as it becomes more and more narrowed, you get these higher pressure gradients with lower volumes. So really the range of disease conditions you want to recreate. We were able to model this computationally, and our computational models, again, for selectively increasing the number of pockets that we would fill. They matched really well with the MRI measurements that we took in the scanner. So the graph on the left shows peak flow velocity for baseline, and then 1, 2, and 3 pockets. And you can see the pink MRI matches the green CFD models very nicely. So this gives us a nice tool for patient-specific modeling. So this is a model to customize aortic flow patterns in vivo to model aortic stenosis and congenital valvular defects, and pioneers the development of high-fidelity models of cardiovascular disease using soft robotics. We hope that this model of aortic stenosis could help with identifying patients for clinical intervention and testing and development of novel therapies. We extended this a little further to patient-specific soft robotic models of both aortic stenosis, but also diastolic dysfunction, where the ventricle becomes stiffened due to constant pressure overload. And here we took 15 sets of patient data. We got it from our partners in the Cleveland Clinic and printed these soft structures of the left ventricle and the aorta that were anatomically accurate, and then built 2 sets of sleeves for each of these patients, and were able to recreate their disease conditions. I'm going to play a 1-minute video and let the video do the talking. This is a video that CNN did in the lab. I didn't talk Irish in it. I sound very American in it, as you will see, but it summarizes the work pretty nicely.
Well, no 2 medical patients are exactly alike, and a new 3D printing project could help surgeons customize their work in the future. CNN's Vanessa Yurkevich has today's Innovate.
A team at MIT is using 3D printing to help reshape medical care by making it more personal.
It would be helpful in planning new surgeries, to understand and see what patients are like individually.
And they're starting with one of the body's most complex organs, the heart. Using medical imagery, a 3D printer builds a customized model heart. It's made of a soft, flexible polymer, but otherwise matches the patient's unique anatomy. A special sleeve puts the model into motion, mimicking the patient's actual cardiac cycle.
We're making it active so that it can contract itself and beat, and then we can change the anatomy of it to replicate disease conditions.
These models will give doctors a better grip on what's happening with the patient's blood flow before undergoing any type of surgery.
Everyone knows with Zoom, it's not the same as seeing somebody in person, right? It's the same thing with surgeons. So the more of a human it becomes, the more information we can get out of it, and better healthcare eventually.
The team at MIT hopes their project will advance how 3D printing can improve medical education and also healthcare in the future.
It can lead to better surgical outcomes, and therefore that is going to improve quality of life. So that was fun. I'm going to go to the last part of the talk, which is more on the focal or local level, where we talk about structural or biological repair of tissue. And this work is very much a collaborative effort with Professor Gary Duffy and Dr. Emer Dolan, who are here. We're looking at moving these implantable reservoirs to deliver therapy or drug, and using this intermittent actuation to modulate the foreign body response that happens when devices are implanted in the body. So we built in this study a dynamic soft reservoir that can modulate the biomechanics of the interface between the device and the tissue, and alter strain, fluid flow, and cellular activity around the implant. When Emer spent time in my lab, she led this study on looking at just applying intermittent actuation every 12 hours for 5 minutes. She was very dedicated. She would do 1 Hertz actuation in this rat study. We did this in a small animal model. And what we found was that in the group that had been actuated, the fibrous capsule that forms around the implant was thinner than the control group. So you can see this in the measurements in the center and the graph on the right. So with the thinner fibrous capsule, you get better therapy transport through the device. So we took this a little further and built a soft transport augmenting reservoir we call STAR. This has 2 pockets, one for therapy delivery and one for actuation. And we used this again in a small animal model. And first we studied how the fibrous capsule forms around it. We used insulin here as an analog to look at function. because we can quantify blood glucose drop and understand the therapy, the transport of therapy out of the device and through the capsule. So you'll note in the top left, if you look at the max blood glucose drop you can get through this reservoir when you deliver insulin, at baseline, it's high, and then at 2 weeks and 3 weeks, it starts to decrease. And that correlates with the fibrous capsule thickness, which increases at 2 weeks and 3 weeks. And you can see this really nice linear correlation between the two. As fibrous capsule thickness increases, you get less blood glucose drop and less efficacy of the therapy. So this study was a long 8-week study. There's a lot of details I won't go into today, but I want to draw your attention to the fact that we can actually use actuation or just this motion, no drugs, to increase the lifespan of implantable devices. So in the control group in the red, you'll note that this is no actuation at all. From 1 to 8 weeks, the time taken to drop the blood glucose by 30% increases all the time. Starts at under 20 minutes, and by the end of the study, it was at 2 hours, which at 8 weeks, it would take 2 hours to drop your blood glucose by 30%, which is not useful. We did another group where we actuated for 3 weeks and then stopped. And right at that 3-week point, you start to see the time taken to drop your blood glucose by the same percentage increase. However, in the group that we actuated for the whole entirety of the 8-week study, which was an awful study for the researchers doing it, Will is here in the corner, that group maintained the same efficacy. You could get a 30% drop all the way to 8 weeks. So we were able to increase the lifespan of that reservoir, again, without any pharmacological agents. So that was great. And then Gary's team, and this is led by Rachel, had the ingenuity to add a sensor layer into the device. So this is a fibrosensing membrane. It uses electrochemical impedance spectroscopy to sense the fibrous capsule that builds up around the device. And if you can know how big the fibrous capsule is, you're able to tune your actuation and do controlled delivery and ensure that you deliver the same dose regardless of what type of capsule is developing around it. So really exciting about this potential technology. Speaking of sensing, this is a bioadhesive that we can use. It's conductive and we can sense ECG on the heart. You can see here, this is done with collaborators at MIT. The epicardial, or the surface of the heart ECG, matches the surface ECG measured on the body. And with Keegan, one of my graduate students, we looked at, could we use this technology to sense arrhythmia and then deliver drug to correct that arrhythmia all autonomously with a sutureless, on-demand drug delivery device. So here is what it looks like now. We're adding functionality all the time, as shown in the bar on the right. We have this bioadhesive electronic interface, and what we can do is sense when the heart rhythm goes too high or too low and then deliver drug to correct it. Here's what it looks like on the heart. You can see it conforms nicely, doesn't require any sutures, and again, the ECG measured on the surface of the heart matches that on the surface of the body. So we did this study where we were able to modify the rhythm and then demonstrate that the device could sense that and release drug. So the RR interval is the distance between the two waves on the ECG. So when heart rate goes up, the RR interval goes down. So we pace the heart, the RR interval drops, and when we stop pacing, it goes up again, and that triggers autonomously the delivery of epinephrine, which then increases the heart rate again. It drops the RR interval. And then you can do manual actuations if you want to further increase the heart rate after that. So it can be closed loop control or manual. Finally, we looked at direct ink writing to create an epicardial patch that could modulate biomechanics. So this is a collaborative effort where we made this adhesive patch. It's strain stiffening, and it can locally modulate part of the heart post-infarct or heart attack to prevent adverse remodeling. So with that, I hope that I have 20 seconds left. I hope that you could see from my talk how we go through this process, but we also learn a whole lot while we're doing it and establish new insights, fundamental insights. Again, I want to thank the team. We recently this week started dodgeball. We, not me, they. We have 3 players from University of Galway, and they won the league game last night. So we're obviously training students to be good dodgeball players too. But thank you for your time, and thanks to this amazing team and my funders.